Okay, now it's time for 4.3, pure pitching motion. Now, if you look at this picture, figure 4.5, uh, you will have theta here. Okay, theta is the pitch angle. It's basically the angle between the x body axis and the x of the um, Earth axis, or okay, xf, okay, the Earth axis. So this is the pitch angle. So, and imagine if it's a model constrained to a pure pitching motion. So there will be no translation. It's just that the aircraft is only allowed to pitch only. So, okay. So the equation of motion can be developed from the rigid body equation developed in chapter 3, okay, previously, by making an appropriate assumption. Okay. However, to aid our understanding of this simple motion, we shall rederive the governing equation from the first principle. Now, the equation governing this motion will be the summation of pitching moment at the center of gravity, okay, is equal to Iy times the angular acceleration, okay, or theta double dot. So the pitching moment m and the pitch angle theta can be expressed in terms of an initial reference value indicated by subscript naught, okay, not the initial, and the perturbation by the symbol delta. So the moment is equal to the initial moment plus the perturbation moment, and similarly for the angle. So if the reference moment m naught is 0, then if this is 0, and the summation of moment will simply be the perturbation only. Okay, so the perturbation of moment, or the change of moment, is equal to Iy times the change in angular acceleration. For the restricted motion that we are examining, the variables are the angle of attack. Okay, the variable inside is the angle of attack, the pitch angle, the time rate of change of this variable. Okay, so meaning that the time rate of change of angle of attack and the time rate of change of pitch angle, or Q, okay, and the elevator angle. So the pitching moment is not a function of the pitch angle, but of the other angle. So the pitching moment is not a function, but the other variables, and this can be expressed as this. So meaning that the perturbation of moment, or the change of moment, is a function of alpha, okay, the change of alpha with respect to time, Q, okay, the pitch rate, and the elevator deflection. Okay, so then we expand into this Taylor series. Okay, so this is where we get our derivative, the del m over del alpha times delta alpha, del m over del alpha dot times delta alpha dot, and so on. So if we align the body and fix frame so that they coincide at t equal to 0, the change in angle of attack and pitch angle are identical. Okay, so meaning that they align the body at fixed frame. Okay, so that they coincide at t equal to 0, then the change of angle of attack, okay, and the change of pitch will be the same, and theta dot, or Q, will also be the same as alpha dot. Okay, and this is true only for the special cases where the center of gravity is constrained. Okay, so if you substitute this, the mathematical model will look something like this. Okay, now we can see that the alpha will be some sort of like x, okay, in the second order of the equation. Okay, so m alpha, okay, this derivative will become like k over m. Okay, the spring constant over mass. Alpha dot will be our velocity, and minus mq plus m alpha will be your c over m. Okay, and alpha double dot will be your acceleration, and this m dE over delta del E, this is the forcing function per mass. Okay, so this is coming from the elevator, because elevator will create moment. Okay, create moment. Okay, so We define as this MQ is the M over the Q over IY, M alpha dot is the M over del alpha over IY, and so forth. Okay. So equation 4.35, okay, is non-homogeneous second order differential equation having constant coefficients. This equation is similar to a torsional spring mass damper system with a forcing function, which was mentioned briefly in the previous section. So the static stability of the airplane can be thought of as the equivalent of an aerodynamic spring, okay, while the aerodynamic damping terms are similar to a torsional damping device. Thus, the characteristic equation of the equation 4.35 will look something like this. So, lambda squared minus mq plus m alpha dot lambda minus m alpha. Inilah equation dia. This is a characteristic equation. So, if you compare with the standard equation of a second order, then we know that the natural frequency is the square root of negative m alpha. Okay. And the damping ratio will be negative mq plus m alpha dot divided by 2 square root of negative m alpha. So this part, negative square root of negative m alpha is the natural frequency, okay, and undamped natural frequency. Okay, 4.39. Okay, note that the frequency is related to the airplane static stability, and that the damping ratio is a function of aerodynamic damping and static stability. So let's get back. What is M alpha? Is a change of moment with respect to the angle of attack. Okay, so we have Cm alpha inside it. Okay, inside this equation there we see M alpha here. So this is the Cm alpha is the measure of static stability. It should be negative. Okay, Cm alpha is negative, thus the negative of alpha we have a positive natural frequency, of course. Okay, and the damping ratio is both, okay, it's a function of static stability and the rate. Okay, function of aerodynamic damping and static stability. So if we solve the characteristic equation 4.37, we obtain two roots. Okay, two roots, following roots, okay, which is this one. Okay, if you simplify, it becomes this. So this is the root. Okay, this is the roots. So one root, this is a real part, and this is the imaginary part. Okay, so we express the characteristic root as this one. Okay, thus the real part is negative this, and the imaginary part is this one. Okay, so which are the real and imaginary parts of characteristic roots? The angular frequency omega is called the diametral frequency of the system, I already mentioned before. Okay, so the general solution equation for this is this one. Okay, it's easier for us to write this way. If you want to write in terms of the derivative, it will be confusing. Okay, so might as well you identify the value of the undamped natural frequency and damping ratio. Okay, so first, then the solution will be this. So general. So what we have here, okay, so the delta alpha over time, the response, the angle of attack, okay, the angle of attack response is the trim angle of attack or the initial angle of attack. Okay, initial angle of attack times all this. Okay, we have now you see a sign, and there is another thing we call phi. Phi is the phase angle, and we have learned before that the phase angle is arctangent of this. Okay, it's a function of damping ratio. Okay, function of damping ratio. So as you can see, recall again that the damping ratio is this zeta is equal to this equation. Okay, and undamped natural frequency is this equation. It's easy, yeah. So it seems that benda ni tak susah sangat pun, senang je. Okay, now let's look at the impact. So this is alpha over alpha trim. So it's basically the original alpha, and this is the response alpha. So what happens is that if you have different damping ratio, you will have a different response. Okay, this is for damping ratio 0.1, which is very close to the undamped, okay, very soft under damp. And as you increase the damping ratio, the overshoot, okay, if it's more than one, the overshoot will be less and less and less, okay. And if your damping ratio is around 0.7, your overshoot will be around maybe 5%, 2 to 5%, okay. And beginning damping ratio 0.8, yeah, your um, overshoot may be zero, close to zero, okay. And this is for, if you look at this, this is for critically damped, okay. So the overshoot is zero, and this is overdamp, okay. For a case of overdamp, 1.5 to 2.0, okay. So this is the impact of damping ratio to the various. Okay, explanation. The solution is a damped sinusoidal motion with the frequency function of Cm alpha and the damping rate function of Cmq and Cm alpha dot and Cm alpha also. Okay, the figure 4.6 illustrates the angle of attack time history for various values of damping ratio. Note that as the system damping is increased, the maximum overshoot is increased. So we don't want to have high maximum overshoot, but we don't want to have overdamp also. It will be very slow response. Okay. Now, if you look at the impact of this, um, in the S-plane, okay, the impact of each one of this, if you look at the solid line, is the variation of CMQ plus CM alpha dot with CM alpha held fixed. So if you fix this, okay, if you fix this, will respond will be this. Okay, as you increase the value of okay, so the influence of this, okay, and the dashed line will be the variation of CM alpha. So if you vary your CM alpha, but CMQ plus CM alpha dot is fixed, it will behave like this as okay. But if you do variation of CMQ and CM alpha dot with CM alpha held fixed, it will look something like this. So what is this? This is like root locus. Okay, this is like root locus. Okay, so you have to study this. Okay, all this to look at the impact of the period and also the time to half amplitude of all these values. Okay, and hence, so for this the period, okay, period of oscillation is given as 2 pi over omega, and the time to double or half the amplitude will be 0.693 over the real value. Okay, the real roots, okay? The real parts of the roots. Okay? And the number of cycle for doubling or having halving the amplitude will be 0.110 over the amplitude of omega over, okay, kappa. All right. So that's all for the pure pitching motion. Oh no, there is another one. Okay. Now, if you have the roots is on the left side, you will have converging oscillation, which it will be damped and will cease after a certain period of time. And if it's the roots are on the right side, it will be diverging and the amplitude will be larger and larger. Okay, so this picture shows the period between the top and the peak and the peak. Okay, and time to double amplitude or half amplitude. Okay, based on this equation. Okay, I don't intend to explain further because the thing is, I think you have to sit down and read. Okay, so that's all for me for point 3 and for this week. So we'll continue next week. All right, thank you.